Recording. All right, I like that. Okay, so 3.5 curve sketching, new year, new font again. My old program that I used to use with all my macros on it, it expired and I can't adjust it here on campus anymore. And that was all Times New Roman. But I can use the built-in editor on Microsoft Word. It's just it takes a little bit of getting used to. So I'm getting used to it, and it uses Cambria Math. I kind of like it. It saves a little bit of space. It's actually a little bit bigger, actually. Garamond is the one that saves space. But anyway, if you see something like this and it looks different than what you're used to, that means it's updated. So what is 3.5 all about? 3.5 is all about bringing sections 3.1, 2, 3, and 4 together, essentially. Because what we've been learning is how to use the derivatives and the function values in isolation to reveal information about a function or a graph or a set of data points. And in 3.5, we're putting it all together to try and come up with a graph, or we're using the graph to answer questions about the function. Okay, so we're going to start off by saying, okay, our ultimate goal is to come up with a meaningful sketch of a graph, and we want to label some meaningful things. So what's meaningful if you have the equation of a function? Well, first of all, the domain, right? That's always the first thing that we look at. Once we find the domain, if we happen to see there's no values that are in the domain, those are possible discontinuities. So we want to find those and name them. Most of the time, they're going to be holes or jump, or holes or VAs. But if it's a piecewise function or jump man, it could be a jump. Number 3, we want to look at the end behavior. That's a real quick thing to do. Is x goes to infinity or negative infinity. Find easy intercepts. The easier of the two intercepts to find is always the y-intercept, right? You just plug in a 0 for x. But if it's factored, we could set it equal to 0 and possibly find the x-intercepts. But if we can't find those, no big deal. Another thing to look at is symmetry. Even functions, odd functions. That might help us, because if we know it's symmetric, even or odd, we only need half the graph, and then we get the other half for free. Now, that all above there that I've been talking through, none of that required any calculus. Some might argue that limits are a little bit of calculus, but really not. We get them in pre-cal. All right. And if we still then have important pieces of the graph that are not revealed yet, now it's time to BOTC. You don't bust out the calculus right away, right? You kind of wait for it. Now it's the big reveal. When we bust out the calculus now we're looking for, where is it going up? Where is it going down? Where is it curved up? Where is it curved down? Where is it turning around vertically? All that good stuff. And then we connect the dots. Okay, that's it. We connect the dots. So here's a classic cartoon from 2008, right? I'm going to the doctor tomorrow, 2 different doctor visits again tomorrow. And perhaps I'll make a little thing out of a coat hanger tonight and walk into my first appointment like that tomorrow and see if Dr. Nelson says, "I'm sorry, I'm afraid your condition is critical." He's a cool guy. He might be in on that, right? He might know. He's had calculus. We talked about calculus before. He said he didn't understand the lick of it, right? Yeah, which is why he became a doctor. That was comforting, right? Okay. Yeah. Anyway, doctors can understand calculus. All right, so let's try it out. Ready? Example 1, sketch the graph of this dude, label in all extreme. Okay, so step 1, domain. Well, when it comes to domain for a non-piecewise function, we're really trying to avoid 3 things, right? Division by 0, square roots or 4th roots or 6th roots or even roots of negative numbers, and logs of anything but positives. Do we have any logs in here? Anyone see logs? I don't. No. Do we have any denominators with variables in it, or negative exponents? Nah. Does anyone see any radicals in there though? Or hidden radicals? Yeah. I see a couple of hidden radicals. In fact, there's 2 of them, right? Are we on cussport? Cussport? They're bigger than 1, right? Very good. But since it's more helpful sometimes for us to think in terms of radicals when it comes to evaluating, you might want to give yourself another version of this function, just to write it back in radical form. 2 different versions of the same thing, not a bad thing. You got options, right? If I was trying to find a y value, I might prefer to plug it into the radical version to evaluate it. But if I'm trying to take the derivative, I'll probably like the original version, right? In fact, if they had given it to me as the pink version, I could discern that the domain is what? What is the domain? All real numbers, yeah. There's variables under the radicals, but they're odd radicals, and we can have negatives under there, and they're not in the denominator, so there's no division by 0. All right, so now we're ready to go. Let's we find the domain. So what else can we find? What else does it say to do? We found the domain. Any discontinuities? No. End behavior? Do we have any? How can we identify the end behavior? That's not going to be real easy here, right? Because if you plug in an infinity, you're going to get infinity minus infinity, right? And that's an indeterminate form. So that's not very, very helpful. Oh my gosh, we're already way down the list here. Find easy intercepts. Okay, let's do that. Let's find the y-intercept, f of 0. That's easy. You're going to get 0 times 2 minus 5, that's 0. So it passes through the origin. We're almost there. We got 1 point, infinitely many to go. What else can we do? Symmetry. Symmetry. Does this function have any symmetry? Well, here's the deal. If it's two terms like this, if you replace x with negative x and neither of the two signs change, in other words, it's the same, it's an even function with y-axis symmetry. If you plug in a negative value for x and both of the terms change, then it's the opposite and it's odd. What's going to happen when I plug in a negative for x? The first term is to the 5th power, so that's going to stay negative. It's going to change signs, but the second one is to the 4th power, which is going to stay the same. So whenever you have one term changing sign and the other one not, there's no symmetry. Well, dang it. That's no help. That's no help at all. We got 1 point out of that whole thing. This problem doesn't do very well in a non-calculus class. Guess what time it is now? It's time to BOTC. Yeah, let's do it. Okay. F prime of x. There we go. I multiply and subtract. So I get 10/3 x to the 2/3 minus 20/3 x to the 1/3. All right. Now I want to see where it's undefined, but it's not. Right. There's no negative exponents there. We kind of talked about that. There's no cusps. And then I wanted to see where it's equal to 0. Now, remember, when it's equal to 0, we're going to try to factor it. So guess what we get to do right away? Factor out least powers. Very good. Now, when you're pulling out a number, you pull out the smaller of the two. So I know I can pull out a 1/3, yes, and I can pull out a 10, right? So I can pull out a 10/3, and then I can pull out an x to the what? Which is smaller, 2/3 or 1/3? 1/3. Boom. And now I like to put the beefy bracket. Beefy bracket, especially when these are fractions. All right, so remember we're dividing. You can imagine that there's imagine that there's an imaginary line there, right? Don't imagine there's a real line there. Imagine there's an imaginary line. 10/3 divided by 10/3 is 1. What's x to the 2/3 divided by x to the 1/3? It's x to the 2/3 minus 1/3 is 1/3. Yeah, it's 1/3. And then minus the next one, when we divide it out, we're left with the 2. Okay, so that's what we're left with. It didn't turn into a nice integer on the inside. But what we have now is a factored version that we can write in a different form if we want. Yes, we can write this as 10/3 times the cube root of x, and then times the cube root of x minus 2. Again, just another version of it. Now you can clearly see here that it's never undefined. Now I'm going to set it equal to 0. And when I set it equal to 0, I'm going to get 10/3 cube root of x equals to 0, or the cube root of x minus 2 equals 0. And now when I solve the first one, I get x equals 0. Yay, there's a critical value, first critical value. And then this one over here, algebraically, we separate, we get 2. And then how do I uncube root something? Cube it. So we get x equals 2 cubed, which is 8. There's the other critical value. Okay, so it's kind of funky math, but no one in here is afraid of fractions. All right, so keep in mind that we do have 2 different versions of the full-fledged factored version. I'm probably going to plug into the bottom one because it's radicals, and I still to this day think better in terms of radicals when I'm evaluating than I do with rational exponents. So now I'm going to come over here to the side of my workbench, and I'm going to set up my number line chart for the first derivative. So we got x and f prime. I got 0 and I got 8. Again, I don't care if you use my version or you prefer like Niskerhak's version, but I'm okay with actually writing numbers in there. I like to see things. So -1, 1, and 9. Remember that you could choose any number in those intervals. There's no discontinuities. Those go in the chart as well, but there's none. And those are the critical values. So pick a number that is easy for you to use. Now I plug it back into, I'm going to plug it into this bottom one. And we just want the sign. 10/3 doesn't affect the sign. The cube root of a negative number is a negative. And on the inside, I get the cube root of -1, which is what? -1, right. And -1 at -2 is negative. So I get a negative times a negative, which is positive. All right, now I plug in a 1 and I get a positive on the outside and a negative on the inside. That's negative. And then I plug in a 9. The cube root of 9 is positive. And on the inside, the cube root of 9, I just got to know if it's bigger than 2 or less than 2. It's bigger than 2. And if you're like, oh, I don't even know, let me change my 9 to something I know for sure. How about 1,000,000? That ought to do, right? The cube root of 1,000,000 is bigger than 2. Okay, so that number -2 is positive. So positive 10. There you go. All right. So these values, 0 and 8, are critical values. Do we have horizontal tangents there or vertical tangents? They were resulting from when the derivative was equal to what number? 0. So those are horizontal tangents, right? Even though they had fractional exponents, we said they're bigger than 1, they're horizontal tangents. So what I like to do, if it's a horizontal tangent, you can only draw a horizontal tangent this way with a continuous function. It has to be curved that way, right? Because if it were curved the other way, if it were curving up and it was a local max, that would be a cusp, right? So there you go. I know it's gonna look, I know I have a local max and I have a local min. I can probably infer the concavity from there if I wanted to. Okay, but let's go ahead and find the inflection points now. Get the second derivative, all right? So now I'm done with this. I'm going to pick up with this version of the first derivative. Time to get some curvature information. F double prime. All right, multiply and subtract. So we get 20 ninths x to the -1/3. Oh, that's interesting. Minus 20 ninths x to the -2/3. There's the second derivative. Now, I already can see that the second derivative is going to have some pivotal values that are in the domain of the function, because it's all real numbers, that make it undefined. That's going to be where the curvature is undefined. That's going to be kind of strange. All right, let's factor out least powers. We can factor out a 29ths. And then which x can we take out? The -1/3 or the -2/3? -2/3 is smaller. Yeah. And then beefy bracket. Okay. And again, imagine that you're dividing right here. So the 29ths divided by 29ths, that's 1. I'm not going to write it. And then x to the -1/3 divided by x to the -2/3, we subtract. This is where you got to be very mindful because there's so many negatives, right? -1/3 minus -2/3 is really -1/3 plus 2/3, which gives us what? 1/3. Good. So that's the first exponent. Minus the other one, we take the whole thing out, and we're left with just 1. All right, now I'm going to clean that up. I'm running out of room, so I'll make a new column. So in the top, I'm going to have a 20 times the cube root of x minus 1. And in the bottom, I'm going to have the cube root of x squared. Times 9. Thank you. Times 9. So that's a good looking version of the second derivative. Did it take a little bit of algebraic effort to get there? Yeah, but imagine if you were doing that with like Greek letters, Greek numbers, wearing a toga, right? Eating a pita, a gyro, right? All right, is this thing ever undefined? It is, right? So remember, your pivotal values are really critical values of the first derivative. So we're going to say f double prime equals dne. And then if you know what the answer is, you could just say when x equals 0. That's the value that makes the denominator 0. If you want to set the whole denominator equal to 0 and then solve for x, you could do that. So that is a pivotal value. It's a possible inflection value. And now we set the numerator equal to 0, but because we're doing it twice, I'm just going to go ahead and set the actual numerator equal to 0. 20 cube root of x minus 1 equals 0. You could have also said the denominator would equal 0 instead of the whole thing equals DNE. But this one we have to do a little bit more work for, right? You divide through by 20, you add 1, and then you cube both sides, and you get x equals 1. There's your other pivotal value. Now, before we set up a number line chart for the second derivative, this is going to be interesting. We know what it looks like graphically when the derivative fails to exist, right? It's a cusp or a vertical tangent. We have a pivotal value at 0 that makes the curvature undefined. It makes the second derivative undefined. What does it look like on a graph to have the curvature undefined? We'll see. We'll see about it. It's probably not going to be as easy to visualize. It's like trying to visualize which dimension was it, Hank?
What was that?
Your math club presentation. What dimension did we go up to? It's like trying to visualize the 10th dimension. It's kind of hard. All right, let's set up a number line chart. We got two pivotal values. We got x and now f double prime. We have 0 here and 1 here. Picking values like -1, 1/2, and 2. And then we plug it back into this full-fledged factored version. Now, notice I don't even need to bother plugging into the denominator, do I? Because it's squared, and there's a 9, and I don't need to worry about the 20. So the sign of the first derivative is determined by the sign of this little factor right here, the cube root of x minus 1. So let's plug in a -1. The cube root of -1 is -1. -1 minus 1 is -2. Negative. If you plug in a 1/2, the cube root of 1/2 is small, right? And that small number minus 1 is what? Negative. Oh. And then you plug in a 2. The cube root of 2 is bigger than 1, right? Or you can plug in 1,000,000 if you want there, and you're going to get a positive number. So interestingly enough, is 0 an actual inflection value? No. The curvature is undefined there. The function is defined there, but it's not an inflection. The curvature did not change there. There's only one inflection point, and it's at 1. So now what we could do is we can come back up and put all this information together. I really have what's that?
We knew that it wasn't a function value already because it was a critical value the first time around.
Because it was a critical value here?
Yes, right? Or no? Can it be both?
Yeah, it certainly can. Yeah, it could be a critical value and a pivotal value for sure. Yeah. So I mean, this is a good one to look at maybe on a calculator afterwards, because what's happening? We have a horizontal tangent at a point where the graph exists, but the curvature doesn't. What does it look like to have a horizontal tangent, but no curvature? That's kind of the 10th dimension. All right. But we do have certain values that are of interest to us, right? Certain x values. Let me go back through and highlight all of them. We know that 0 is a good one, 8 is a good one, 0 again is a good one, and 1 is a good one. Now that I have collected all of my meaningful candidates, let's go back to the original function and find their graphing partners. Yeah, the y coordinates that go with them. All right, we already found 0. And now let's just go ahead and plug in 8. F of 8, going back to the original problem. Oof, okay. So when I plug it in, do I want to go 8 to the 5th first or go to the cube root of 8 first? Cube root of 8, which is 2. 2 to the 5th then is 32. Okay, boom. Minus 5 times the cube root of 8 again is 2. 2 to the 4th is 16. All right, now let's simplify. We get 64 minus 80, which is -16. All right, so we have the point 0, 0. We now have the point 8 common -16. There's one other number, 1, right? Let's figure out what f of 1 is. F of 1, if we plug it in, that's easy, right? That's 2 minus 5. -3. So we have the point 1 common -3. Now, that might seem like an arbitrary thing. That's supposed to be an 8. There we go. It might seem like an arbitrary thing to the non-initiate, why we're plugging in an 8 and a 1, right? It might just seem random because that's what an algebra algebra 1 student is taught to do, right? Just make a T table, come up with a bunch of random X values, plug them in, plot them, connect the dots. But we're doing it more judiciously, okay? These are the chosen ones, if you will. All right, now we'll put it all together to make a sketch. So now we come off to the side. All of our information is there and we sketch it. So let's see, we need a y-axis, we need an x-axis. Let's go ahead and plot the points here. 0, 0, got it. 8, negative 16. So I'm just going to say that's down here. And then the point 1, negative 3, which should be, I'll just say is right here. So I'll say this is negative 3 and this is negative 16. So not drawn to scale, but it is labeled. Now notice what I could do. I could also move this entire thing over a little bit because most of my local behavior, most of my detail is over here. So I'll just kind of adjust it. All right, now we can connect the dots. There was a question on the 3.4 worksheet where it's asking you to determine where a function was like both increasing and concave down at the same time. This might be a helpful thing to do. We have two separate number line charts there, each giving us different pieces of information, but there is some overlapping, right? So if you want to, and this is not required, I'm going to borrow this space up above here. Sorry, Courtney Gibbons. If you want to make like a super number line chart, an SNLC, Saturday Night Livecast, right? You have your X values here, right? And you could do F prime in the top and you could do F double prime in the bottom. So let's put our values on there. We got 0 and we've got 1, which is close by, and we've got 8. So what you're putting on there is your critical values and your pivotal values. And now we just fill in the blanks. To the left of 0, I know that the first derivative is positive. Okay, I know that between 0 and 8, the first derivative is positive. So it's positive here, positive there. I'm sorry, between 0 and 8, it's negative. All right, so there's a partition in the middle from where it used to be, but that's okay. And then to the right of it, it's positive. And now we'll come back and put the concavity information on there. To the left of 0, my concavity was negative. Between 0 and 1, it was negative. And then everywhere to the right of 1, including to the right of 8, it was positive. Okay. So what this does is it just helps you organize what's happening on each interval. This basically tells you how to connect the dots. All right. Does everyone see how I made that number line chart? You just go back to your other two charts and you're going to have to, like, in some case, jump over. Remember what we did in the previous example where we had the circle and we just kind of labeled what the sign of the first and second derivative were? This tells you what to do, right? So you can even like help yourself underneath there if you want to draw what it looks like, okay? If the first derivative is positive on an interval and the second derivative is negative, it has to be increasing concave down. So increasing concave down, that's the only way you could draw increasing concave down. On the next interval, it's negative, negative, so it should be decreasing concave what? Down, decreasing concave down, so it's going to look like that. On the next interval, it's negative, positive, so that's decreasing concave up, decreasing concave up. And on the last interval, it's positive, positive, that's increasing concave up. So you could do that. All right. And now we can connect the dots like that. All right. So here we go. Here's my final graph. I'll use red. It's coming in. And I know now that I have it curving downwards. And there's a local max at the point 0, 0. And then it's decreasing concave down to the next point. And then it's decreasing concave up to the next point. And then it's increasing concave up after that. Now, if you look at this, the way we drew it, it looks a whole heck of a lot like a real handsome cubic polynomial, doesn't it? There's no cusp or anything on it. There's two horizontal tangents. It looks like a cubic polynomial. What makes it different from a cubic polynomial is it's not as symmetric. It's a little more bunched towards the local max. And then there's this odd thing. This is how we drew it at 0. There's a local max there, but the curvature is undefined. Does that look any different from a normal local max where the curvature is defined? Normally we would say it's concave down there. So if we were listing intervals of concavity, we would have to step over that value because it's undefined there. All right. And then we're done. So this one problem kind of encompasses everything that we've done so far. There were no discontinuities on it, unfortunately. That's what the next one kind of has, and some others, but that's bringing it all together. And that's about the most difficult algebra that you're going to have. You can factor out least powers. If you know how to find where the derivative is undefined, you should be good. All right. So I'm not going to go ahead and do it, but you can answer all the questions now. Where is this graph increasing? It's where the first derivative underlies positive. Where is it concave down? You would have to step over 0 because it's undefined there. Okay, so you can write all that up. And you can justify local max, local min like we've been doing. I'm curious what the graph would look like, because we're just kind of playing it by ear. It's kind of I guess, an artistic piece instead of an actual mathematical piece. But if we graphed it on the calculator, I'm curious what the calculator would give us at 0. Does that mean we have 30 minutes left? Yeah, okay, thank you. See, one problem took the whole lunch, right? But we did everything. We did everything that we've done so far. All right, I'm curious. Let's type it in. So 2x to the 5 divided by 3rd power minus 5x to the 4 divided by 3rd power. And let's see, I have a window over here. Let's just go window. I'm going to my window manually. I'll do like -5 to, where was that other point? 8. So we should go to 10. And then y min, I have a local min of -16. So, oh, it's going super fast. I can't change it. Why is it going so fast? Uh-oh. I can't actually, let's just hit graph. For somehow it got accelerated. Yeah. All right, but this is enough. I was really curious what it was going to do at 0. Do you see that? Let's do this. We can do something else. I'm going to analyze this. We don't use this that often, but if you go to second zoom, you can go to your format and you could turn, if you can, go to the second one. It won't let me. Oh, there it is. I did fast. It's like playing a video game. I went down to the right. You could turn your grid off, your coordinate grid off. I messed it now. Oh, it's the third one. I'm sorry, it's the third one. I did it before I got to the bottom. Okay, now watch. No, I didn't. No, I'm doing the wrong thing. Oh man, second format. I want the grid off. Axis off. That's what I want. I want the fourth one. I wanted the fourth one, but I can't go straight there. Oops. Turn that back on. Grid off. Oh, axis off. Oh. Anyway, okay, I'm just gonna go to it. Look. Do you see what's happening there? If you were to look at this, you might think there's a sharp turn there, right? But it's not. Y'all were able to do it on y'all's. I don't know why it's going in super speedy ROM mode. Yeah, it is Mach 10. The best I can explain how to visualize the 10th dimension, or what does it mean to have, it's a smooth enough turn. It's a smooth enough turn that it's a horizontal tangent line and not a cusp. But it turns so sharply that the curvature gets blown out, right? I don't know. That's the best way I can describe it. The curvature is undefined there, but the function is defined, and there is a horizontal tangent. Is it?
Yeah.
Yeah. Okay. So anyway, the way we graphed it is fine, but in hindsight, maybe we should have had it, now that we know kind of what the actual values are doing in the neighborhood of it, it comes up like this and then turns real sharp, but not sharp enough to make a cusp, just sharp enough to kill the curvature. I don't know how else to explain it. It's kind of an oddity, but it exists, right? It's like a blunt point. I don't know if you're talking about that. Right. Okay. If I would have said blunt point in any other class but this one, people would have gone, oh, you said blunt. Right? But not y'all. All right. Comments or questions on that? Who's the immature one? Yeah, the guy talking right now. Yeah. All right. Okay. Let's do this. Let's do this. In the last 30 minutes, let's look at an actual AP question from 1982, shall we? Like almost 40 years ago. Really 40 years, because it happened in May. We're in January. 40 years old. It's an oldie but a goodie, right? All right. So you have an average like 15 minutes to do it. So let's see if we can do it in about 15 minutes. 1982, right? We're sitting there. We listened to Debbie Gibson on the way to, no, we listened to Men at Work on the way to the test. No, we were listening to Iron Maiden's first release off of their Peace of Mind album, The Trooper, on the way to, there we go. Given that f is the function defined by this, f of x is x cubed minus x over x cubed minus 4x, find the limit as x goes to 0. Find the limit as x goes to 0. Oh, we got this. We got this. Never not first. Now, notation, notation, notation. The limit as x goes to 0. I'm going to go ahead and write the actual expression in here. And I plug in and I get what? 0 over 0. Hey, we have two ways to eradicate that. We can either FADO it, right? Factor and divide out. Or we have this new tool discovered by Johann Bernoulli called L'Hopital's rule. I think I'm going to use that. Lop it, right? And so we're signaling our intention. Did they have L'Hopital's rule back in 1982? They did. 3x squared minus 1 all over 3x squared minus 4. And now we try plugging in again and we get what? -1 over -4. Can we leave it like that on a free response? Yeah, you don't have to simplify. Notice I'm working straight down. If I'm using L'Hopital's rule, I'm showing the direct substitution off to the side and I'm labeling that I'm lopping it. Okay. And of course that equals 1/4. So if you're not going to be able to sleep at night, you can do 1/4, but you get no bonus points for that. Free response. Now, the other way you could have done it just for kicks and giggles is you could have factored out the x and then you get x squared minus 1 all over factoring out the x. Then you get x squared minus 4 and then they divide out and then you plug in, bless you, to what's left and you get 1/4. So that's another method. This is what I called back in the day the FADO method. But remember all those methods, lick them over, lick them, Ratcon, FADO, Sledgehammer, those were all just ways to eradicate 0 over 0s primarily, sometimes infinity over infinity. In all those cases, then L'Hopital's rule would work. All right, so I don't have the scoring guidelines for this, but here's the deal. If we get all the points, we don't really care at this point where they come from, right? All right, and then I shrink that down. Okay, letter B, find the zeros. Another name for the zeros are the roots or the x-intercepts, right? How do we find the zeros of any function, whether it's f, f prime, or f double prime? Do we plug in a 0 for x? No, we set it equal to 0. Yeah, that's why it's called 0. So again, if you want to say f of x equals 0, like today in the modern age, that would be enough to earn a check. But because we actually have to manipulate it without a calculator, you could just go straight to this step, set it equal to 0. Okay, either one of those gets the step. Now I'm running out of room, so let me bring all this over here. In order to find the zeros, I could just set the numerator equal to 0, right? But that would be kind of very perilous, wouldn't it? We haven't even considered the domain of this yet, have we? It didn't ask us for it. We got kind of jolly and happy and started finding part A. What is the domain of this function? Yeah, x can't be 0. In fact, the entire denominator can't be 0, which means you factor out the x, you get x squared minus 4 can't be 0. So x can't be 0, -2, +2. So this is you taking quick inventory before you even jump in. Look before you leap, as they say. So it's the set of all x such that x is not 0 and plus or minus 2. Now, since you find the discontinuities, you might see if they're wholes or VAs. How can we tell that? Well, you can either use direct substitution, because if you get 0 over 0, remember it's a whole. And if you get non-0 over 0, it's a VA. I know that when I plug in a 0, I get 0 over 0, right? So I know this is a whole. And if you plug in -2 and +2, you get non-zero. So these are both VAs. Okay. So that's the first thing I would do. Just mentally take inventory. Now, why is that important? Well, if you had used L'Hopital's rule on part A to find the limit, you may set the function equal to 0 right here. And then, of course, a fraction is equal to 0 when the numerator is equal to 0. Yes? You don't have to say num equals 0. You just do it. And then you factor out and you get x equals 0 and then x equals plus or minus 1. If you walked away from there, you might be like, man, this problem's easy, right? But are all three of those actually zeros? No, we already know that 0 is not in the domain. We already could figure that out. So you could stop right there. If you cross out the 0, they know not to count it. Your bottom line then is your final answer. You don't have to list them as ordered pairs. Okay, so that could be the extent of your answer. Now, if you did it with the Fado method, or you want to continue to do this, what you're left with, I'm going to call it y equals x squared minus 1 over x squared minus 4, except we have a hole at 0. Once you get rid of the hole, you can use what's left for the rest of the problem. It knocks it down, right? Because the only difference between f of x now and y is the hole at 0. Okay. So we answered the question, what are the zeros? Here it is. All right. Now, if you had done the Fado method up above, you wouldn't even have to necessarily show that you're setting x cubed minus x equal to 0. You could have just done what was left, right? The x squared minus 1. I can't shrink it down. Oh no, what a problem to have. Oh, there it goes. All right. So far, so good? Have we BOTC'd it all yet? No, not at all. Not at all. So you're like, dang, excuse me, Proctor, Mr. Proctor, I think I'm in the wrong test. I think this is the Algebra 2 test. Oh no, you're in the right test. I've already prayed for you, Mr. Carnsey. Write an equation for each vertical and each horizontal asymptote. Hey, we've already got that information in part over here, right? La, 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 la. Good thing we're used to finding domains first and figuring out what the discontinuities are. Okay, so here we go. The function's name is Frank. So we're going to say f has vertical asymptotes. We can't use VAs on the AP exam, darn it. As vertical asymptotes at x equals -2 and x equals 2, comma, and a horizontal asymptote in France. No, how do we find horizontal asymptotes? They're not discontinuity asymptotes. Remember, they are end behavior asymptotes, right? So for horizontal asymptotes, all we got to do is find the limit as x goes to infinity of f and the limit as x goes to -infinity of f. Now, you wouldn't even have to show this analysis unless the question said, show the work that leads to your answer. That's typically what they say. So if you know that you're just looking at the end behavior, you can do one of two things. You can look back up here to the original expanded version, or you can look up here at this condensed standard version. But remember, this is where you analyze how fast the top grows compared to the bottom. Yeah. And there are three cases. Either the top grows faster because it has a larger degree and there's no horizontal asymptote. The bottom grows faster because it has a larger degree and it goes to 0, or they have the same degree and they grow effectively at the same rate, in which case it goes to what? Leading coefficient over leading coefficient. And it doesn't matter which expanded version you use. In either case, you get 1, right? And a horizontal asymptote at y equals 1. If it asks you for the analysis, this would be if it said to show the work that leads to your answer. They usually say stuff like explain, justify, and show the work that leads to your answer. Okay. All right. So this was 1982, 40 years ago. They might up their standards since then, right? I know I've upped mine, right? Back then, all I needed was a G.I. Joe and some oatmeal to keep me happy. 1980. Boy, I remember 1982. I lived in Westlaco, Texas. All right. What a great city. Describe the symmetry of the graph. Justify algebraically. Crap, I was already to say the graph is symmetrical like a monarch butterfly emerging from its spring cocoon. Right? Although there's monarch butterflies now, right? I don't know much about them, but I know that monarch butterflies have made a comeback this year. They're thriving more than ever. That's good. Justify algebraically. So what they're asking for you is this. Remember f of negative x. If you get the same thing, plus positive x's and negative x's give the same y value, then it's even, right? But if you get the opposite, then it's odd. And if it's neither one of those, then it's no symmetry. So let's look at, we found a hole, didn't we? There was a hole at 0. Okay. So if there was just a single hole and it was like at x equals 1, but there wasn't one at x equals -1, you would already know there's no symmetry. Okay. But being at 0, it could have folding symmetry. So for this, since I want to consider the entire function, I would go back to this version here. Okay. Just because I want to make sure the hole is considered. So here we go. Let's say f of negative x equals, and I'm going to plug in a negative x for every x. So negative x cubed minus negative x all over negative x cubed minus 4 times negative x. All right. So they don't really do this much anymore. 40 years ago, this was kind of a big deal, but it's worth reviewing. Okay. So all I did is I put parentheses where x's were, and I put a negative x. All right, now let's evaluate. The first one, the sign's going to change, right? A negative number cubed is negative, so it's negative x cubed. The second one, the sign is also going to change. It's to plus. All over, the sign changes, and the sign changes. Now, you got to be careful here. The sign in both in the top change, so it's an odd function, right? Remember what I said term-wise? If both signs change or all the signs change, it's odd. If none of them change, it's even. In the bottom, both signs change. So the bottom is also odd. Guess what an odd function divided by an odd function is? It's an even function. In other words, you can factor the negative out of the top and the negative out of the bottom, and they'll divide out, and you're right back where you started. So that's really about all that you have to do, other than say this. I'm trying to cram this in here. They want you to kind of complete your vertical analysis. Okay. So then I would say this equals f of x. So f is an even function, and we better be thorough, an even function. Let's go ahead and say with what type of symmetry? Y-axis symmetry. Now, because it only asked you for the symmetry, you could have just said, so f has y-axis symmetry. Again, this is kind of an old type of problem. So that's kind of good to remember. Odd functions act like negative numbers. Even functions act like positive numbers, right? So a negative divided by a negative is a positive. So an odd divided by an odd is an even. If one in the top were an odd, all the signs changed, and one in the bottom were even, none of the signs changed, then it would be essentially a negative divided by a positive, which is negative. An odd divided by an even would be odd. Okay. So anyway, that's just helpful. And then using the information found in parts A, B, and C, sketch the graph. Okay. They haven't had students sketch graphs on free response questions in a really long time. Now, what does that mean? That means that has it gone away forever? Or could it be that this is the year they bring it back? Bring back the graphs. Bring back the graphs. Okay. All right, let's see what we've got so far. Let's go back over here. Okay, on part A, we found the end behavior. The limit, or no, we found the limit as x goes to 0. And it was what? What was the limit? It was 1/4. What does that tell us about the graph? We know there's a hole at 0. Do we have the coordinate? If I approach x equals 0 from the left and from the right, I'm approaching the y value of 1/4. Guess what I know? I know the function has a hole at 0, 1/4, right? Is that something we can plot? Yeah, I'm going to come over here to 0, and I'm going to put a giant open circle, and I'm going to call that 1/4. Okay, so even though it's not a point on the graph, it's a location that I can use to target. Okay. Okay, so that was part A. There's a hole there. The zeros, did we have any? Oh yeah, we had 2 of them. -1, +1. So I'm going to try to draw it somewhat to scale. So here's -1, here's +1. Those are x-intercepts. Those are the zeros. Okay, got those. So far, so good. Hey, look, does it kind of look like it's shaping up to be symmetrical? If I were to draw these the same distance away? Yes, right? Okay. Yeah, that's looking good. Looking good. So that's what I took from part B. And you see what I'm doing? I'm going back to each part and saying, what did I find? How can I use that on the graph? What did I find? How can I use it? Asymptotes. Oh, yes, -2 and 2. So here we go. Here would be -2. Here over here would be +2. And then right. Maybe that's what they did. That's what they do in my head. All right. And there was another thing we found out there. There was a horizontal asymptote at 1. So let me extend my graph up here. Let's see. Go to 1, 1, 4. Okay, here's 1. I'm going to call that 1. And then horizontals make different sounds. Kind of like horses galloping. All right. Hey, so far so good. Looking good. Looking good. And then what did I find over here? Symmetry. Symmetry. Okay. So it looks like it could be symmetric, right? Easily. That's why it said to justify algebraically. Now, I'm guessing on part D, if you didn't know how to justify it algebraically, let's say you skipped it, but you started plotting information that you found and you got to this part on E, you might say, well, by golly gee whiz, this looks like it's shaping up to have some y-axis symmetry. You would retreat back to part D and say F has y-axis symmetry, and then say, but I don't know how to justify algebraically. I'm guessing that question was worth 2 points. One for the answer, one for the justification. If you knew that it was symmetry on the back end, could you come back and reclaim that 1 point? Absolutely, right? Don't ever, ever, ever surrender. Anything is better than nothing. Nothing is the surefirest way to get 0 points. Put something down. If you only know the units of something, as long as they're attached to a random number, you could get the unit point. So put your birthday and then put like feet. And by birthday, I mean like 27 feet, not like January feet, right? Okay. All right. That's all we found. Is this enough to sketch the graph? I'm guessing they think so. So remember, the evidence is not just what's there, but what's not there. So I know, and I haven't done any first derivative, second derivative number line stuff. So I'm just using the fact that the graph is going to look like this. I'm guessing, right? I'm guessing. And then what's happening to the left and right of 2? Is it going to live above the horizontal asymptote or below? If you're in doubt, just plug in any number to the right of 2 and see if it's bigger than 1 or not. But if it were to live below, you would see another x-intercept that we already would have found. So that's the evidence that's not there. It has to live above. And of course, if it lives over there, it lives over here. Now that's my best guess. When it comes to the middle, how do I know that it goes down instead of up? Well, if it were going up, here's really the only other option. It would have to like bounce here and then do that and then bounce here and then go up. That's really the only other option because it can't, there's no more x-intercepts, right? So the only thing it can do if it's not crossing is bouncing. And there's no way to bounce from below and go through the hole. So when in doubt, you can go with either the simpler version or you could do a little bit of analysis. If I knew what it did immediately to the left of 2, I think I'd know the answer, right? So let's just review that. Let's say that you had this question, the limit as x approaches 2 from the left of f of x. We studied this in 1.3. How do you find limits at a vertical asymptote? Well, if you were to plug into the original function, you would have gotten non-zero over 0. Okay, so you know, oh, it's DNE, right? If it's a free response, it's DNE. But it's DNE because it's some type of infinity. I just need to know which type. So let's come back up here to this version. I'm sorry, this version. We don't need to worry about 0. We're well to the right of 0. This version is easier to use. What do you get when you plug in a value that's just to the left of x equals 2? And remember what I said, just to the left would be like 1.9. Just come to 10. What do we get in the top? 1.9 squared is bigger than 1. So the top is going to be positive. 1.9 squared in the bottom is going to be bigger than 4 or smaller than 4? It should be smaller, right? Because 2 squared is 4. It's going to be 1 point. It's going to be smaller. A smaller number than 4 minus 4 is negative, and a positive divided by a negative is negative. So I know this answer is negative infinity. Where the heck did I write it? I got so much going on. Oh, there it is. It's negative infinity. Okay, so that's how you can figure it out. You plug in, you get non-zero or 0. You know, there's vertical asymptote. Plug in to get the sign immediately to the side you're looking at. So now I know for sure that it looks like what I have there, right? Yeah. Not really, I guess, kind of. There's something else I could do with the first derivative. I mean, there really are some quite elaborate possibilities. It could do this and then do this, right? And in that case, I would have so many different horizontal asymptotes. So you could actually take the first derivative and see how many critical values they are. But that's not the point of this question back in 82. Let's talk about how many critical values there are. I didn't take the derivative, but I could tell from the graph how many critical values this function would have. How many? Does it have any critical values? The vertical asymptotes are in the domain. Normally at 0, we would say, hey, there's a local max, but there's no dot anywhere else. So it's not even in the domain. So there are actually no critical values. So if you wanted to, if you had time, you could take the derivative, see where the numerator was 0, and there would be no solution. Okay. All right. I think that's enough for today because those were the 2 curve sketching examples. What we're going to do tomorrow, then, I'm not going to be here tomorrow. I'll just let you know. I have 2 doctor's appointments tomorrow. Tomorrow, we're going to sit down and we're going to take a test that a substitute's going to hand to you, and it's going to be a memorization test. And it's 1.1 to 3.4. So I have it made out. I already added it. Let me see how many questions are going to be on it. I have it right here. It's 1 page front and back. It's an experiment in saving paper. I'm hoping that there's enough room on here for you to fill in. If not, you can grab paper from over there and say, see attached and number it, right? Right. But like, it's like hey, what's the Pythagorean identity that has cosecant in it? List it. Yeah. How do we know if a particle changes directions from the velocity function, right? How is the slope of a tangent line related to the normal line? Inverse functions at corresponding points have what? Oh, there we go. There's a freebie. There's a freebie. The Hody-High rule, right? In terms of F and G. State the EVT in if-then form. State the MVT in if-then form. State Rolle's theorem in if-then form. State the IVT in if. God, this is a nice test. What 2 types of numbers do we put into any number line chart? First derivative number line chart. Critical values and discontinuities. What types of numbers do we put into a second derivative chart? Discontinuities and what's the word I gave them? Pivotal values. There you go. There you go. Yeah. What's the, yeah. So you're gonna have to know what's the derivative of log base b of x? 1 over x divided by the natural log of b. What's the derivative of b to the x? B to the x times the natural log of b. What if I throw absolute values around the log's argument? They go away, right? What else is on here? What's the Taylor form equation of a line? Oh, that's a good one. Yeah, what's the derivative of arc cosine? Ooh, oh, nice. Ooh, yeah. How about this? When you have a derivative that's a quotient, you get horizontal tangents when the what? When the numerator is 0, and you get vertical tangents when the denominator is 0, and you get no tangents when what? They're both 0, because that gives you like a cardioid cusp. Yeah. How do you know if 2 functions f and g are inverses of each other? What happens when you compose them? F of g of x will equal g of f of x, and they'll both equal x. Yeah, yeah. Hey, what if at any given time c, velocity is positive and acceleration is negative? Then the speed is whating? Decreasing. Okay, okay. What's the derivative of secant? What's the limit definition of the derivative? What's modified form? What's alternate form? Oh, this is so good. Yeah, this is so good. All right. There's 66 questions. You have an hour to do it. Do you want to take it during A lunch? So if you need to borrow some from C, or do we do A lunch as study? You got advisory and A lunch. All right, so advisory study, A lunch study, then you got 1 hour to do 66 questions. I asked Mrs. Skurhawk when she gave it to her class with fewer questions, that if they know it, they finish with plenty of time to spare. So no, that's less than a minute per question. How long does it take to write Hody High minus Heidi Hover Ho Ho? Yeah. Oh yeah, soccer's out again, right?